Okay, let us start with mth band, or I would say Nyquist M filters. So, these are special filters that you would often see when you will have to deal with topics where sampling rate converters or multi-rate operations and some of these concepts would be involved. So, the motivation to Nyquist M filters stems from polyphase decomposition. So, from polyphase decomposition, we can write the filter h of z as some constant c plus a delay with the first polyphase component z power minus 2 h2 of z power m, so on, m minus 1 units of delay with I think this must be E1 here, just okay. So, h of z can be written as c plus z power minus 1, E1 of z power m, z power minus 2, E2 of z power m, and so on and so forth. Now, when we look at the output, right, when we say if I have some signal x of n, that is possibly upsampled and goes through this filter h of z, and I get y of n. So, my y of z is basically x of z power m times h of z, and I could now interpret this as using this filter h of z. This is c times x of z power m plus summa L equals 1 to m minus 1 z power minus L E L of z power m times x of z power m. Now, let us consider the first polyphase component, which is what we have here, right. So, we can interpret this relation as we have x of n, and when you upsample it you get y of n. This is a scalar, this is basically like a gain parameter. If you just ignore this gain, if you take x of n, if you upsample you get this component x of z power m, right. If you downsample this signal, then you will get x of n back. So, therefore, the relationship between this component to y would be y of m n is x of c times x of n. by considering just the first polyphase component. Okay. Now let us go a little further. Suppose h of mn is C when n equals 0 and 0 else. Right. The first component is the first sample for this filter is non-zero and everything else is 0. So, from the representation of h of z in the polyphase form, we can consider the following summation: h of z omega power k for k equals 0 to m minus 1. Let us say, and we could interpret this from our DFT, if you can recall, right. These were basically translation of the frequencies, right. Take integer multiples of the frequencies and then translate the spectrum. This is what it is. Let us add all the translated responses and see what really happens. So, we start with k equals 0. When k equals 0, it is basically our h of z, which is c plus delay E1 of z power m plus dot 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 plus z power minus of m minus 1 E m minus 1 of z power m. So, for k equals 1, we have h of z omega, which is going to be c, plus you plug z equals z omega here, we have z power minus 1 omega power minus 1. This omega is basically the nth root of unity. You have E1 of z power m omega power m plus dot 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 z power minus m minus 1 omega power minus of m minus 1 e's of m minus 1 of z power m omega power m. This is the k equals 1 term. You do this till k equals m minus 1. So, you have c, this is a DC term, plus z power minus 1 omega power minus of m minus 1 E1 of z power m omega power m minus 1 times m plus dot 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 z power minus of m minus 1 times omega power minus of m minus 1 times m minus 1 times e subscript m minus 1 of z power m times omega power m minus 1 times m. Okay. Now, we add up all these quantities. So, this is going to be c added m times plus. So, if you look at this term here, E1 of z power m, you have E1 of z power m times omega power m is basically 1. Similarly, if you just take integer multiples of those they will all be 1. So, you will have even of z power m appearing outside. So, you will have a z power m z power minus 1 times you have to add 1 plus omega power minus 1 plus dot 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 omega power minus of m minus 1 times you have even of something plus these terms. So, if you just notice that these are basically the inverses of the roots of unity, and since they form a group, you will circulate back the same elements again. So, this vanishes. So, this is going to be 0, and you can conclude with similar argument that the rest of the terms also vanish. So, all you would be left with c times m. Now, if c is chosen to be 1 upon m, this would imply that the summation k equals 0 to m minus 1 of the base filter and all the translates, that is m minus 1 copies, this basically is going to evaluate to 1, which is basically a flat response. But what is the physical meaning of this thing, right? So, that means I start with a base filter h of z, then I look at all its translations at multiples of the base frequency, right. You have e power minus j 2 pi by m, j 2 pi by m square, cube, so on, right. So, all integer multiples of the frequency. So, then which means you are basically shifting, you start with the base spectrum of h of z, then you are shifting the spectrum and then you are summing all of them, that is what it means, and that should be flat, that should sum to 1. And why do we need this kind of response? Imagine when we started off with this QMF property, right. I have a good low pass filter, a good high pass filter, and we said basically I take the sum of the responses of the high pass filter and low pass filters at the quadrature frequency. There could be certain artifacts, but I really want the responses to sum up to 1, and any deviation that I have would be basically some sort of distortion which I would want to minimize, perhaps using Johnston's filters and so on and so forth. So, if I look at all the sum frequencies across all the translations, they have to add up to 1, and each of these individual filters are basically M band filters or Nyquist M filters, because each of them correspond to a certain band of frequencies that they are tuned to. Okay. So, if you think about the frequency response, you can say my scale is not perfect, but I hope you can appreciate what is happening here. So, you may have, so let us say this is h of z, this is possibly h of z omega, so dot dot dot, this is h z omega square and so on. Somewhere we have to have 2 pi, this is 0, this is frequency responses. So, now we know the criterion that we would want some filter h of z to satisfy if the sum frequency responses have to be 1. That means one such filter could be the Nyquist M filter, which is of the form C plus delay times the polyphase version plus 2 units of delay followed by the second polyphase dot dot dot. Okay. And a special consequence of these filters, a special case I would say of these filters are the half band filters. So, as the name suggests, this is a special case of the Nyquist M equals 2 filters. So, therefore, we can expect h of z to be of the form c plus delay times some E1 of z square, where E1 is the polyphase component. So, therefore, h of 2n is c when n equals 0 and this is 0 otherwise. It is not too difficult for you to see because these are all odd polynomials, right. You have z square, z power 4, z power 6 or z power minus 2, z power minus 4 if you want to bring in other powers, negative powers, and therefore, this is going to be odd because you have a one delay component outside. So, basically the even component is basically when n equals 0 it is c is 0 otherwise. Is a special case of the general Nyquist M filter. There are plenty of examples for such filters and let us go through some of them. Say suppose h of z is 1 plus z power minus 3, your polyphase component E1 of z is basically z power minus 1, just a delay. I could have z plus 1 plus z power minus 1, wherein E1 of z is 1 plus z, which is anti-causal, and I could have something like this where E2 of z is, I will have to say E1 here just to be consistent, E1 of z is 1 plus z power minus 1, and in this case this filter is causal, in this case this filter is anti-causal. So, the filters themselves could be causal or anti-causal, but they all have linear phase. Now, as it suggests, let us verify if the responses sum to 1, let us sort of verify. So, we take h of minus z, which is h of E j pi minus omega, and h of E j omega plus h of E j pi minus omega, this is equal to 1. This means I look at the low pass response. If h of z is a good low pass filter, this is a good high pass filter, right. If you had a Nyquist M filter, you will have various band pass versions in the middle. So, this plus this basically sums to 1, and this is symmetric about pi by 2, and you have a case for basically mirror symmetric filters here. Okay. Now, I think with these filters in mind, I think some important notes that we need to kind of bring in. One can design good half band filters endowed with mirror symmetric properties, and we saw in our homework exercise how having mirror symmetric properties will help us simplify our computations, right. So, basically we can build good half band filters using these, and second, the generalizations to Nyquist M filter design can be carried out through optimization techniques. We saw the case where we could set up our optimization problem for solving for the base filter that led to Johnston filter, and the same idea you can extend this towards Nyquist M filters. So, these are some basic filters that you will see in multi-rate operations.